So we have a very, very cool lecture called The Past, Present, and Future of Computing in the Twilight of Moore's Law. Okay. And again, I prepared this lecture a few months ago for a general conference. So it's high level, but with some technical detail. So I hope it will be very interesting. So if you guys did any of my courses in the past, you'll know that I like history. So in my opinion, animation didn't work, but okay. To understand the future, we should start by going back in time. Right? Now, is there anyone in this room, I know some of you are young, who doesn't know why I put this picture on? Eliana, you've never seen Back to the Future? So your homework is, first of all, go see Back to the Future. Anybody else hasn't seen Back to the Future? You can skip 2 and 3. Okay. So starting really, really long time ago, what we can call, I would say, the first digital computer and the first analog computer are shown here in the picture. So on the left side here, we have what is known as the abacus. Now, I'm sure that all of you had this in kindergarten or in like 1st or 2nd grade, learning how to count and so forth. But actually, the abacus was invented really long time ago, about 2500 BCE, and was prominently used up until, I would say, the Middle Ages or something like that. And there are claims, even though I traveled all over China and I never saw one actually being used for calculation, but there are claims that even till today, people like in markets will use them. When I was traveling around China, they had little pocket calculators that when they'd hit a button, it would say the name of the number in Chinese. But the top abacus here is what's known as a Chinese abacus, and the bottom one is known as a Roman abacus. And you can really do all kinds of very complex computations with these things. You basically count to 5 or something with ones, and then you count how many 5s you have, and you can do all kinds of really nice multiplication and more things. And I think it was Richard Feynman who was traveling around, I think in Africa, and he came to a cafe or something where people were calculating with abacuses, and he bet them that he could calculate faster, I think by hand or with a calculator, and they were able to beat him with every type of thing that he tried against them. Even though he was this great scientist, he just wanted to see that they were so fast in using the abacus. So I would call that the first digital computer that ever existed. On the right side, anybody know what this is? Okay, so yes, it's called the Antikythera mechanism. But has anybody ever heard of it before? So see, I'm already teaching you something. So in about the year 1900, something like that, people were diving off the coast of Greece, and they found this weird thing that you see here inside a boat, one of the shipwrecked boats from about 2,000 years before. Okay, and they realized it was something different than they'd seen before. But the year or so after that, when they were studying this thing, they found there were gears and wheels and stuff, and understood it was something that was not really known back then. Within the years when they were studying this thing, trying to figure out what it is, they understood it was a computer. And as recent as like the 90s, I believe, they used 3D X-ray to figure out exactly what was inside and how this thing worked. And it was a real analog computer that could figure out where stars were, where the moon was going to be, and so forth, used for navigation. And they believed that there were several of these things, but nobody knew that this level of computation existed so long ago. It was a huge breakthrough. It's a real fascinating story. If anybody has time, I really advise you to go and watch a Discovery Channel or something like that show about it. It's a fascinating mechanism. So that I would call the first analog computer. But computers really came into their modern way with the guy here on the right, who's Charles Babbage. Who's heard of Charles Babbage before? So we have a few hands, that's good. Charles Babbage is known as the father of the computer, and it's pretty amazing, his story too. So he was a guy who was working in a place that was checking almanacs. Who knows what an almanac is? So an almanac is a book that has tables upon tables of where different stars are supposed to be in the sky throughout the year. Okay, this is something that when I was in the Navy, I learned how to use it. That people would stand on their boat, okay, in the middle of the night and use a sextant and look where a star was and look up in the almanac and find a number and use something on a map. It's a really long and hard process. And it would always come out when I knew that I was in Israel. I would find myself, you know, in like South America or something because it's really inaccurate. But people who were good at doing it would navigate that way and figure out where they were in the sea. Okay. But it's really important that the numbers inside there are correct. And to do them, you have to solve all kinds of polynomial functions. The problem was that he took almanacs from different providers and they were checking to see that the numbers are the same. But there are thousands of numbers in these books. And they were finding out that all the numbers are different. There are so many typos and so many mistakes. And Charles Babbage sat and said, this can't be. We have to make some sort of automation that will calculate these numbers accurately and print them out in the book so we won't have these mistakes. And he came up with this thing here that you see on the left-hand side over here, which is called the difference engine. Okay, this is only a part of the difference engine. He went to the British government and asked for a grant to build this type of a machine so people wouldn't get shipwrecked because they didn't know where they were in the middle of the sea. And they gave him, I think, from what I remember, something like 1,500 pounds, which nowadays would be like $150,000 or something like that, but still a substantial grant to go and build it. And he tried to build it for about 10 years, from 1823 to 1832. Finally, arriving at the most he made was this, which is a small thing like this big of all these gears, okay? And the problem was that the mechanical engineers could not make fine enough parts at the time. And the guy who was working with decided to quit on the project and he just gave it up. Why did he give it up? Because he had a better idea. He said, okay, I can go and calculate with my difference engine, which is now called difference engine number 1. I can calculate polynomial equations up to like the 7th order or something. But I can't do general purpose type of stuff. I can't do real computation. So he thought, and he came up with this thing called a store, where numbers are saved, and this thing called a mill, which processes numbers. Does that sound like anything that we know from life today? A memory and like a CPU, right, and a data pack. And he came up with this thing called control flow, where you can actually tell the mill what to do and go and store numbers and bring them back. And he called this thing the analytical engine because it could do analytical calculation. And he drew up all these books about how this worked. But the British government said, no, we gave you all that money and you just wasted it and didn't build anything. We're not giving you any money or money. He had I guess he was a big professor or he was a famous guy, and he had one of his proteges was a lady named Ada Lovelace. She happened to be the daughter of the Lord Byron, who's a very famous British poet. And Ada Lovelace was studying this machine that he made where he had written how you could kind of write some sort of a procedure on it. And there was a thing that all mathematicians knew back then called Bernoulli numbers. I don't know if we ever learned about this in one of our early mathematics classes, but it was something that all mathematicians knew. And she wrote down a process how on the analytical machine, which was again only in the book and in Charles Babbage's head at the time, how you could figure out Bernoulli's numbers by doing some iterative process. That is nowadays considered the first computer program. Babbage wrote kind of a computer program, but it was just a real simple thing. The first non-trivial algorithm or computer program was this thing that Ada Lovelace wrote down. And has anybody ever heard of Ada Lovelace? So other than or and in Lior, Ada Lovelace is nowadays being really recognized over a lot of things because not only was she the first programmer ever, she was a woman. And in fact, NVIDIA just came out with a big chip last year, I think, called no, sorry, that was Grace Hopper. I just made a mistake with that. But they've been recognizing Ada Lovelace because maybe she was like 200 years old or something. And one of the first object-oriented computer languages is called Ada. named for her. So she's a pretty important person, and she was doing that on Charles Babbage's machine. But Charles Babbage didn't get the money, and he never built it, and so forth. Then he got tired, I guess, with the analytical engine at some point. And in 1847, he said, well, I'll take some of the ideas that I came up with the analytical engine, and I'll improve that difference engine because they're still printing almanacs with all kinds of typos. So he went out and he drew a whole set of how he's going to make this amazing thing called the difference machine, the difference engine 2. But the British government didn't give him any money, and he died. And then his son tried to come and have it built, but he wasn't able to get the money or something like that. In 1985, a guy who was at the who was the curator of the British Museum, found the manuscripts that Charles Babbage had drawn up how the difference engine number 2 was supposed to look and work. And he went and he just made this life project of building the difference engine. And he finished it 12 years later in 1997. And now there are 2 of them, one in the British Museum, British Science Museum, and one in I think in the Computer History Museum in San Francisco. And you can go and see this big machine. It's pretty big. There's a great YouTube video of a tour guide showing how he puts in the function, the coefficient, the function that he wants to find out, because again, it calculates polynomials up to the 7th order. He turns these gears, these things that we have over here, like they're in decimal, they weren't in binary. This is, I think, even before Boolean algebra was invented, but they pass on the equation over to the next gears. There are a whole bunch of set of gears. I don't know if it's 7, but maybe even more. And finally, they have this arm that comes down and prints a number on a piece of paper, and at the same time on a mold for creating more books with. So it has a printer too. And this works, they say, almost without a bug from his drawings. So it's pretty amazing. It's really nice. I also advise you to go and look on YouTube. So Charles Babbage was such a genius, and he was so much the forefather of everything we have today in computing that when he died, he said he gave his brain to science, and there was a big fight over it, and somehow they split his brain into 2, and half of it is this picture over here, which I think is in the British Museum, and half of it is somewhere in the US. Okay, so you can go, I went and I saw his brain. So if Babbage was the father of computing, I guess Turing is what you would call the whole brains behind the computer. He is the man of the computer. So I'm sure that many more of you have heard of Turing because there was a movie about him not long ago, right? Maybe 2 of you. Has anybody here not heard of Turing? You've never heard of Alan Turing?
Oh, I thought you said, has anybody here about
No, not heard of Turing. And I don't know why somehow I didn't ever learn in my undergrad, and it's missed by a lot of people. There's this concept of a Turing machine that I was never taught. Okay, so who knows what a Turing machine is here? Very few people, which is strange for people who finished their undergrad in engineering. But a Turing machine is this weird type of a picture that we have over here on the screen. It's this concept that he wrote when he, I think, was a PhD student, okay, of an infinitely long piece of tape that has symbols on it. Let's say 0s and 1s, okay? And there is the scanner thing that's over here. There's this position where the machine is at, and the position reads if there's a 0 or 1 or some other symbol like the A's and B's and C's here on the tape. And according to what it reads, it changes or doesn't change the thing that's underneath it and moves to another spot on the tape. Well, it turns out that this weird thing that I just described here, or you see in the picture that's moving over here, is a machine that can calculate anything. And there's a proof that says that any machine that can implement a Turing machine is what you call Turing complete. And to be a general purpose computer, you must be Turing complete. So Turing conceived what modern computing is, basically. And it turns out that Charles Babbage had already designed the machine that was Turing complete. It was never built. the analytical engine, but he drew it up. He drew thousands of pages of how to build it and so forth out of mechanical things. But Turing came and he thought of this mathematically or theoretically and described what is needed. Turing, as you guys probably all know, after a stint in the US, decided to go back to Britain for several reasons, but one of them was to help in World War II. And they basically built around him a secret like base or a research center called Bletchley Park, where his main job was to break the code of the Enigma, which was the German encryption machine. And he built a real computer, or he was one of the designers of a real computer there that was kept secret until the 70s. So it doesn't get like the fame that some of the other computers we'll look at got. But the Colossus, which was his computer, was one of the first electric and programmable computers, probably the first programmable computer there was. And Turing's brain and his amazingness was able to actually break the code of the Enigma in the end. Unfortunately, Turing was gay, and that was not accepted those days in Britain. And they tried to give him all kinds of remedies for being gay, and instead of taking them, he, according to the stories, he was a big fan of Sleeping Beauty, I think, or Snow White, and he killed himself with a poison apple. And who knows what he would have achieved in his lifetime if he had lived to an older age. But Britain at least put his face on the 50-pound bill to repent for their sins. So Turing was the brains behind the computer, but the real computer that was actually came into the world, or at least was considered for a long time the first ever computer, is the Eniac. And the Eniac was built in 1945 by Eckert and Mauchly, two guys, or they led the project at the University of Pennsylvania. Okay, and the Eniac is considered the first programmable electronic and general purpose computer. Okay, I don't know if I'm recording this. I think I forgot to. So the Colossus that Turing built, it was there for only calculating certain mathematical functions. It was not general purpose. Eniac was the first general purpose one, and it held a patent for being the first, and Colossus was secret, so no one knew about it. So Eniac held the patent for being the first electronic computer for many, many years, until these three guys, Attensoff, two guys, Attensoff and Berry, who were at Ohio State, I think. They had the Attensoff-Berry computer, the ABC. They said, we built an electronic computer before you did. They sued them, and in the 1970s, they revoked the patent of Eniac. So it's not considered the first computer anymore. But their computer was not. This is the first Turing-complete computer, okay, that was in existence. But this thing was huge. It had 17,000 vacuum tubes. Vacuum tubes, we'll see in a minute, they're these light bulb type things. They take up a lot of power, okay? And when the computer was switched on, the lights in Philadelphia dimmed. It took, I think, 200 kilowatts or something of power. Okay. It was programmed with cables. To put in a new program took about 3 weeks to put it in and debug it. All right. And they had a group of 6 women, okay, who they were the programmers. But they also had a whole team of people who would run around looking for light for one of the 17,000 vacuum tubes that blew out, and they had to change, and it could take 3 hours to find and change a vacuum tube when it would stop working. But this was about 1,000 times faster than any other computation that could be done at the time. Working on Eniac, Eckert and Mauchly understood that they couldn't have this type of thing where you had to go to program the computer and move all these cables that takes 3 weeks. That's ridiculous. So they thought of this concept of, instead of that, using some sort of a memory and storing your program inside the memory. And they wrote up an idea about it. And a big research group, I believe, research like a think tank in the US, brought together the best minds in America to go and build their idea of this stored program computer. And this project was called the EDVAC. And one of the guys who was in this team, but he was kind of an outsider on the team, was John von Neumann. Von Neumann is a Jewish guy who actually converted to Catholicism at some point. And he was considered like the brightest mathematical mind of his time. Okay. And von Neumann was also a big personality. And he ran around and he was in the Manhattan Project, and he heard that Eckert and Mauchly's in the project, they were gonna, provide this great computer, and they needed it for the Manhattan Project. So he went in, he joined the project, and he saw this idea that they were writing about stored program computer. And he said, that is brilliant. And he wrote down a paper, a draft of a paper, and sent it to a friend. The friend took it, typed it up, a friend or a colleague, I'm not exactly sure, and called it first draft of a report on the EDVAC. But he wrote that the author was John von Neumann without mentioning Eckert and Mauchly. He sent it around to many people around the scientific community. This thing was never patented. But nowadays we call a stored program computer what? A von Neumann computer. Did von Neumann invent it? No, but he got all the credit. And Eckert and Mauchly were not very happy about it. Okay, so, but von Neumann was a brilliant genius in his own, and he found out a lot of things, but he got credit for what we use nowadays, a von Neumann architecture, which actually was not his. He was a part of the project, but he wasn't the mind behind it. All that was very good. So we had these computers, they were electric, but they were crazy. They took a ton of power. They would burn out. It wasn't something that was like scalable. Okay. In those days, you had a vacuum tube, which was this big, expensive light bulb that was your radio, for example, was one of these. So you had a radio sitting in your living room. It was like the size of a TV set, and everybody would sit around and listen to the radio. And if it would blow out, it would cost you all your money to go and replace this vacuum tube and so forth. There was a guy named William Shockley, who was one of the best engineers of all time and a crazy guy, but besides his personality problems, he had been looking for a replacement for the vacuum tube for many years. During World War II, he had to revert to other work. And coming back to it, he was already a big boss at Bell Labs. Bell Labs is where everything was invented back in the day. And he had these other two guys working under him, Bardeen and Bretagne. And they decided to go and do a side project, kind of, or not exactly look at what Shockley was looking at. And they almost not accidentally, but not really with his authority, they found out a way to make what is called a transistor. And as you can see here, what we have is these two gold electrodes over here, a piece of germanium, and this, according to lore, is an office, an office pin type of thing, where they needed some sort of connector, so they just found what was on their desk to use it. A paper clip, exactly, a paper clip. And they stuck it all together, and what this was able to do was to replace the triode vacuum tube, which was what was being used in those days to operate the Eniac and other types of computers. You needed something that could have an external control over current. So we had what was called the emitter and the collector, and current goes the opposite way. So the current would run through from one electrode to the other through this semiconducting material. And according to a third electrode, which is not part of this, you could make this current strong or weak. If it's on or off, it becomes a digital switch. If it's a bit stronger or a bit weaker, it's some sort of an amplifier, an analog switch or an analog amplifier. The difference between this and a triode vacuum tube was that the triode vacuum tube, it worked by making this big electric field with lots of voltage, and adding something else to it would cause like electrons to fly through a vacuum. It was really hot. It needed a lot of power. With this, it's a solid state device. In other words, nothing changes here. There's something in, as you guys all know, the energy band gaps that allows the electrons to go from side to side or stop. This is not a BJT transistor for everyone thinks it is. It's what's called a point contact transistor. And this was considered probably, or considered in a lot of circles, the greatest invention in history. Yes?
How small was it compared to the cube?
Good question. It's not substantially smaller, but the amount of, I mean, this was a prototype, right? This was the first one they built. Okay, number one.
The size of the fist.
Yeah, but that's what the size. I mean, a triode, there are different sizes, but that's also, it's something that's big, right? But this was, it didn't need as much power, and it didn't heat up, and it didn't burn out. Okay, that was the big thing here. And the transistor is something that they were looking for in Bell Labs and probably other places around the world for years. And Shockley himself had been looking for it. Now, the big problem here was that Shockley didn't invent it. And Shockley, he was the genius, and he was the leader of the team. He was the manager. But this was his invention, right? He'd been working on this for years. It was his dream. And not only that, in the famous picture for that they took, I guess, I don't know if it was for the Nobel Prize or just for announcing the invention, Shockley is sitting here, you know, touching the actual stuff. That's almost like me going and sitting on the machine while Yoav is looking from behind, okay? Bardeen and Brattain were the guys who got their hands dirty. Shockley was standing by, you know, he was managing the project. And they were even working on something he wasn't aware of exactly when they found it out. And he is the one in the middle. So they got pissed at this picture. And Shockley was terribly jealous and pissed that even though he got credit for the project, it wasn't him. He wasn't the guy, and he had to be the guy. So Shockley went and he left Bell Labs, okay? And he started his own company or his own research lab called Shockley Laboratories at a bigger company called Beckman Coulter. But I just want to show you the timeline. So the vacuum tube was invented in the early 1900s, and the triode, the one that has it can work as an amplifier or a switch with the third electrode, because most of these things were originally diodes. But the triode was invented in 1906 at AT&T. Bell Labs is part of AT&T, by the way. Okay. This is the point contact transistor, which we saw was invented in 1947 and is considered maybe the biggest invention in modern history. And then Shockley left and went to Beckman Coulter because he couldn't stand it that he didn't invent the transistor. And he knew that there were many problems with that point contact transistor. And he knew that he had an idea that was better. He just wasn't able to do it before the war. And he built his own team and his own company or his own research lab inside Beckman Coulter until he came up with the bipolar junction transistor, the BJT, which some of you may have seen or heard about, which really solved a lot of the problems with the point contact transistor, and was able to take computing and scaling and transistors into another level and turn it in from a great invention into something that was a product that could be sold and put out on the market, and put a radio instead of on our living room table into our pocket, okay? And make a computer that was much, much, much smaller than and needed less power than something like the Eniac. But Shockley, as I said, was a really tough personality, okay? And he was a horrible boss, and everybody hated him, but he had great people around him, okay? And at least 3 of those people, I can't remember all, but 2 of them at least, okay, who were Gordon Moore and Robert Noyce, but there were a total of 8 that decided one day that they couldn't stand Shockley anymore. They thought he was managing the company wrong and taking the great science that they were making and not using it right. And they got up and they moved out of Bell Labs, which I think is in New Jersey, moved across the USA into the California area, and they opened a company called Fairchild. And that is the birth of Silicon Valley. And they are called the traitorous 8 because Shockley couldn't stand it, that these 8 leading engineers on his team got up and left. And they started Fairchild. And at that time at Bell Labs, not in Fairchild, another guy invented this thing called the MOS transistor, which had lots of problems because the fabrication wasn't good and it didn't work well. But it was this idea of a different kind of transistor was invented in those times. So I decided to put it on the timeline at that point. And lo and behold, 8 years later, those two, Robert Noyce and Gordon Moore, along with Andy Grove, decided to leave Fairchild and start their own company, which was called Intel. And this whole scaling thing that you see here, I accredit it to Intel, and Or will be happy with that, even though it doesn't work there. Okay, so that's kind of the evolution of the electronic switch. However, all of this was worthless without these two guys, Jack Kilby and that same Robert Noyce, who was the CEO of Fairchild. Afterwards, he was not the CEO of Intel. Gordon Moore was at the time, but they took the idea of the transistor and made what possibly is the more important invention, even though the transistor is the most important invention ever. But they did something more important. They took that transistor, which was an independent element, and they found out how they could build an integrated circuit. So Kilby was a young engineer who had joined Texas Instruments, and according to the story, he didn't have enough vacation days. And Christmas or Thanksgiving vacation came along, and he couldn't take vacation because he hadn't accrued enough vacation days. So he sat at work and came into work when everybody else was away, and he decided to play around in the lab. And somehow while he was playing around in the lab, he built this weird looking thing over here on the left, which was then patented as the integrated circuit. Okay, but to make an integrated circuit means you want to put several devices on the same substrate. And that's what he was able to do. He was able to show how he could make with a single process several devices, more than one, which was up till then making the BJT transistors by sticking together pieces of semiconductors, how he could make on one substrate the whole transistor and several of these transistors. He had two problems. He didn't know how to make isolation between the transistors. So what did he do? He took a knife and cut. Okay. And the other thing was he couldn't connect the two things. So what did he do? Took a wire and connected. Robert Noyce, who was the CEO of Fairchild, was thinking about this, and a couple of years later came up with this idea. Well, he read a paper and he productized it of how he could make isolation using reverse bias p-n junctions, and how he could connect the different devices through metallization. And so these two guys are recognized as the inventors of the integrated circuit, even though there are two other guys who maybe would also be considered as the fathers, the guy who invented the metallization, the isolation, and somebody else. Unfortunately, Robert Noyce passed away in 1990, and they don't like engineers on the Nobel Committee, but they finally gave Jack Kilby the Nobel Prize in 2000 for the invention of the integrated circuit. They only give it to people who are alive, so Noyce couldn't. And that leads me to Gordon Moore. He was Robert Noyce's one of his partners in founding Intel, one of the traitorous 8 who left Shockley for building Fairchild. And Gordon Moore was the CEO of Intel, and this you've all seen, but just to remind you, he wrote a paper in a magazine called Electronics in 1965, where he said, look, when the transistor was invented, there was 2 to the power of 0. There was one transistor that we could make. A few years later, we got the integrated circuit, which we can already put, 2 or 3 transistors, resistors, capacitors on the same substrate. At this point in 1965, we can already put 2 to the 6, 64 transistors on the same substrate. And he writes in the paper, it's very readable. It's actually an economic mixed with scientific type of a write. He writes how he thinks that it is economically and technically possible to keep at this level of doubling the number of transistors every couple of years for the next 10 years. And that way, for 10 years, if every year we double the number of transistors, we have 2 to the power of 16 or 64,000 devices on one substrate in 1975. And that sounds like a crazy idea, but he explains why technically and economically it's worth it. The thing is that he never thought that this would continue for the next 50 years. And is it over? Because, as he said here in ISSCC 2003, no exponential is forever, and all of us know from the COVID pandemic, the reason that we're standing here without masks on is because no exponential is forever, right? And you see that all of these experts, which are some that I just found from snippets, I mean, you have here, you know, the CEO of NVIDIA, and you have here professors at MIT, all saying that Moore's law is dead for the last 10 or 15 years, okay? And as an undergrad student, I heard some guy in the hallway speaking English to two foreigners who were visiting him and looking at something, a big famous physicist. And I was listening to the English. He said, 90 nanometers, we've reached the height of lithography. We can't go any farther. This is the minimum pitch. Moore's law is dead. 90 nanometers. Remember when that was? A long time ago. And as Gordon Moore said, forever can be delayed. Okay? So no exponential is forever, but it can be delayed. And that leads me into how have we and how are we going to overcome the challenges? So we finished the history, and now we're going to the present and a little bit of the future. And we'll start with photolithography. So I'm just going to remind you that what photolithography is. We start with this substrate, usually silicon. We cover it with some photoresistive material. We bring some sort of a photomask, some sort of a light source. We start shining light on it until we develop this the feature that we wanted, that we cut out on of the mask onto the photoresist, and then we clean it away, and now we can do whatever we want underneath this blockage, or you can do it the opposite way too. That's the basic idea of photolithography. The problem is that photolithography, and we'll be discussing this a lot next week actually, the critical dimension, or the difference between two, the size of a feature that you can print, goes by this equation. Okay, so that's the minimum pitch, this d, and inside we have this lambda, which is the wavelength. And so you would think that you just take a light source that has a shorter and shorter wavelength, and then you can get a smaller and smaller resolution. But if we look at a graph here of how photolithography is advanced over the years, you will see that we got to a laser of 193 nanometers 20 years ago or something like that, and it hasn't changed. And the reason it hasn't changed, or there are several reasons it hasn't changed, but even making this 190 nanometer laser, you need this huge and really expensive machine with really big lenses, and it has been a challenge that everybody knows we want to go past that 193 nanometer wavelength. And that's why that guy, that professor, was saying 90 nanometers, we reached a peak, we did all the tricks we can't go any lower, Moore's law is dead. Well, guess what? Seems that process engineers are smarter than that professor, I guess. And a few of the ways that we've gone through this. So one of them is immersion lithography. So as you can see here, there's this n in the denominator of our equation. And the n is usually like air or vacuum, which is at 1, but we can use something else like some sort of a liquid that has a larger n, and therefore we get a smaller d over here. So that's one thing that they've been doing for many years already. Another thing is playing with the phase of the masks. So you can change the phase of the light that goes through the masks, and then use additive or subtractive refraction to get better resolution. Okay. The thing that really has helped for the last number of years is what we call litho etch, or pitch splitting. And again, we're going to be discussing this a lot next week, which means we use two masks that are at our minimum resolution, but we put a little shift in between them, and then we can get half of the resolution between the two masks. And that's really nice, and it worked for a while as well. We can even do it litho etch, litho etch, litho etch. But what's really brought us to be able to print up to 7 nanometers with 193 nanometer laser, which is completely ridiculous, right? Is what we call self-aligned double or quadruple patterning. And again, we'll be showing how this works next week. So these are tricks that have brought 193 nanometer laser up till today. However, it's not enough. And finally, in the last couple of years, maybe 2, we've been able to productize, as if I did it, right? But the world has been able to productize, and mainly this company ASML, which whoever bought their stock in the last few years has become a very happy person. They've been able to productize the extreme electroviolet laser. It's a really huge machine. See the size of the guy here? It doesn't use photo masks. It uses these reflective masks. It's because the 13 nanometer light wave does not go through like the type of glass that they use for masks. So finally, we have these much better features. The
absorption is just too intense for it to be able to use refractive techniques, so we use reflective.
Okay, thank you. It has improved the features a lot. So the features look much nicer, which gives us less variation and better modeling and so forth. But the main thing maybe that it does from a perspective of the fab is that it reduces the number of masks, because we needed a lot of masks to do all those double and quadruple patterning. And even though it costs a lot to buy one of these things, we need a lot fewer masks, a lot fewer steps. We can make the chips faster and get the chips in the end to be worthwhile. I wouldn't say cheaper, but to get them to be at a price point where people like Apple can pay for them. That being said, it's not enough, or can say yes or no, but they've started using double patterning and so forth on EUV. And actually, the real amazing thing is that they now have something called a high numerical aperture EUV that has come out, which is something like a $250 million machine that ASML has put out, and TSMC and some others have bought several of them. I mean, that's like, okay, that's like a lot of money. And so they're supposed to be able to make even better, resolution. So that was photolithography. So we've solved photolithography. It's not our problem. We know how to print things real small, okay? But another problem was the gate oxide. So if we have our standard transistor here, so this is the MOSFET, which is what enabled scaling to replace the BJT. As you all know, we have the substrate, we have the gate, and in between the gate and the substrate, we have this little teeny thin piece of oxide. And we know that the capacitance of the oxide goes according to some sort of a coefficient, kappa, or it can be different names, times the permittivity of the basic permittivity here, divided by the thickness of the oxide. And what we need is that Cox to be as big as possible. Why? Number one, it affects our transconductance. How much current we can get out of the transistor for each bit of voltage. And the transconductance, if you guys remember, is the mobility times the Cox times the width times the length. So we want this to be as high as possible because that's the gain of the transistor base. The other thing is that we have the subthreshold swing, which is how good a switch this is. How much we can turn off the transistor. And again, here, we want this C oxide to be as large as possible to make the subthreshold swing as small as possible. So we really want this Cox to be as large as possible. So what did we do? We scaled over the years this Cox. We made it smaller and smaller, figured out how to build really thin layers, and got to, a really small point of 1.2 nanometers down around 65 nanometer technology. The only problem with that is at that level, we have tunneling through the gate. And so our transistor, instead of just going from the source to the drain, now we have leakage or almost current, especially if we go any smaller than that, going from the gate to the channel or to the substrate. Just so you understand, it's about 6 atoms or something of silicon dioxide to do this. So this was infeasible, okay? And that was another thing that was supposed to break Moore's law. So for many years, we again, I guess, worked on solutions. And the thing is that you can take this kappa over here, this K, okay, and look at different materials, and you see that if silicon's dielectric constant is 3.9, you can take a material like hafnium dioxide, which is already at 25. Okay, and if you're able to go and increase the K, you can make the Pox much larger and keep the same transconductance and the same subthreshold swing, and thereby both reduce the gate leakage while achieving the same results, and then maybe scale it a bit too. But the problem is that the whole reason that MOS technology actually works and is scalable and so forth is because they were able to build such a nice oxide, because the silicon connects really well to silicon oxide at the interface. And now we're going and putting something else there, and that doesn't work well. And so it took about 20 years to get to this, that they could put in what we call high K materials. Not only that, they also changed the gate, and we'll explain why next week, to a metal gate. Okay, and so really in 45 nanometers at Intel, they started using high K metal gate. And I think in TSMC it was at 28, maybe at 45 as well. And we get a lot reduced leakage. So we did something really crazy, is we took the silicon dioxide out of the CMOS process, which was the basis of the CMOS process, but it worked, and that's what we're kind of still doing now, as we'll see next week. Next problem. Our next challenge is leakages. Remember, we're talking about how we overcame the challenges or are still overcoming the challenges. So, as probably everyone in this room knows, that our transistor is supposed to be off, but it's actually kind of like a faucet that's dripping water. Okay, so we have all these leakages that are going through the MOS transistor at all times, and it got to be such a problem that around 2005 or so, 90 nanometers or 65 nanometers, in a lot of different chips, the static power, the leakage power, which is supposed to be 0 and was always considered 0 for a MOS transistor, actually overtook the dynamic power, and this issue of dark silicon really became a huge problem. So what are we supposed to do with that? Well, luckily we have this guy over here. This guy's name is Chen-Ming Wu, and you don't see his name at the bottom, but the reason I decided to put his picture on top of all others is because he is behind, he's a professor at Berkeley, now retired, he's behind the two most, I guess, important inventions in this field of trying to reduce the leakage. The first one up here, and I'm going to mention it first because we're not going to talk about it afterwards, is what's called ultra thin body fully depleted silicon insulator, or FDSOI for short. And so that is one of the types of transistors that he invented. It's actually what you could call a back gate transistor or a double gate transistor, where we make the transistor, instead of on a regular substrate, we put a piece of silicon dioxide underneath it, or we use a wafer that has it like that, and it has a very thin body, so the drain and the source are fully depleted all the time, and this is able to reduce leakage in all kinds of ways, because leakage can't go through that big piece of oxide underneath, and because we're able to actually bias the gate in a way to change the threshold voltage. So that's one thing, and mainly ST Microelectronics and a bit Samsung and a bit Global Foundries have been selling this type of transistor for the last few years, and it's one of the one of the technologies that's used for a lot of the low power devices and a lot of devices for like space type applications as well, because it's more resilient to soft errors. But the one that really won is his other invention, which is called the FinFET, which was an idea that came up at Berkeley, and they started working on already in around 1999. It was a DARPA project, that very big project, and it took about 12 years to bring it from this idea that was shown in the lab at Berkeley until they were able to fabricate it in a production level way. When Intel always gives their own names for things, they don't use the actual name, so they call it the Tri-Gate. I think everybody in Intel nowadays calls it a FinFET, but they used to say, don't say FinFET, just like Apple didn't like us to say iPhone X, they wanted us to say iPhone 10. So Intel wanted us to say Tri-Gates when it was actually the FinFET. Okay, so Chen-Ming Hu is the guy who is behind this. And what the idea here is that we have 3 sides to the channel here. So you get much more of this, of these electric fields that apply the field effect and are able to shut off the channel and stop the current from going through it. So the FinFET basically from Intel 22 nanometers and other foundries 16 nanometers is the only way that we make transistors today. And really our lecture next week is going to talk all about FinFETs and how they're made and why they work and so forth. But FinFETs are also reaching end of life now at around 5, 3, 2 nanometers, depending on what you call the technology node. It doesn't really matter the name, it's just the generation of the technology node that's currently being developed and put out by the different foundries. And what seems to be the winner of the next type of transistor that's coming out there, which I can ask or afterwards how it's made, because this is pretty crazy, are these nanosheet FETs. Intel, of course, doesn't call them nanosheets, they call them nanoribbons, but they are these type of wide nanowires. As you can see here, what you have here are stacks of a metal gate surrounded by the oxide, and surrounded by, when within it we have the silicon channel. So you have these 3 layers, but the silicon channel and the oxide are actually hanging in the air during fabrication, because remember, we fabricate things from bottom up. And I looked at some papers trying to understand how this is made. I didn't spend that much time on it, but I really don't know how they make it. It's pretty crazy. They somehow make the structure and then they etch out somehow the stuff in the middle and fill it up with other stuff. It's really weird, but it's pretty cool that this is actually what's done. And here it's what you call a gate all-around transistor. So if in the FinFET we had 3 sides, the 2 walls and the top as the gate, which made the electric fields, now we have it from the bottom as well. So really each of these wires is completely surrounded by a gate, and we can really turn off the transistor well, get lower leakage or better ion to eye-off ratio, and that's what is supposed to drive the next few, and maybe last, I don't know, pure, I would call it CMOS FinFET type of designs. There is another way of doing it, which is called a vertical nanowire, where we build the nanowires standing up, and then it's easier to surround them by this gate and an oxide structure. But as far as I know, none of the announced technologies from, again, mainly TSMC and Samsung and things that have been demonstrated by IBM are using this vertical nanowire type structure, even though they've been researching it for many years already. However, there is a next step. Everybody's looking for what's next. And if you look at IMEC, which is a Belgian research institution that really comes up with a lot of the ideas that then go into our technologies at Intel and at Samsung and TSMC, they are talking about already for the next generation is what they call a fork sheet, where the 2 different colors here are because you have a PMOS and NMOS transistor on 2 sides of the gate, which can really somehow make like a CMOS within a much smaller type of area. What we've been doing actually is what is called design technology integration, where we're trying to not scale anymore the size. In fact, feature sizes of the gates have stopped scaling for the last, I don't know, 10 years or something like that, maybe a bit less. but really they got stuck around 14 nanometers. And all the rest of the names are just ways of getting more density of our standard cells and our SRAM. So one of the ways is this fork sheet, and these have already been demonstrated in lab, and they're probably in a year or two or something, TSMC or Intel or somebody is going to announce that they're already production ready and they're getting good yields. Of course, the amazing material of the future is the carbon nanotube or graphene, which are basically the same thing. The carbon nanotube is a rolled up sheet of graphene, which is a 2D material. So any of these 2D materials, which is basically one level, one atomic level, have all these very cool characteristics. So you can either, it's been shown that you can use graphene as the channel material, or you can use carbon nanotubes as the channel material. And they even do have companies that are producing products. I don't know exactly at what level, but they have been around for more than a year or two and have funding and so forth. So these are possible things that we're going to see in another few years down the line inside our machines that are going to make them go better. There is what's called a TFET is one of the things that's been researched a lot and is one of the possible candidates to replace the MOSFET, even though, as far as I know, for some reason, even though it seems more simple to someone who's not a device physicist like me, it seems more simple than other things like putting carbon nanotubes inside, but it hasn't found its way into one of the roadmaps of the big foundries. And the crazy kind of way of looking at it, and this is something that I know that at Berkeley they showed this even probably 10 years ago, and there are companies that are trying to do this in many research centers, are these piezoelectric FETs, where it's really a mechanical switch that is your transistor. And so you can actually kind of like push or pull mechanically on the channel. And this is something that's really crazy. It's like making a real machine, but at the nanometric scale, and it has much better ion-I-off ratios in theory than all of the different type of electric field-based transistors that we've seen. So that is how we stopped leakage, or how we're dealing with leakage. And the next question is what sells the computers, and that's performance. Okay, so we all know that we buy computers for performance, and the amazing thing is that Robert Dennard, who was a very important engineer at IBM, he's actually the guy who invented the DRAM. He came up with this model in a paper from 1972, where he said, look, I'll explain to you why Moore's law works. He said, if we take our transistor and we take each of the dimensions we have in the transistor and we scale each of these dimensions by the same amount, we can call it S or something like that. And I see that some of my math type symbols didn't appear here, but or K we can call it, I guess, or S. Then what will happen is that the next smaller device will give us this amazing thing. So if we take 1 over K to be 0.7 or scale by 30%, and we apply it to all these different dimensions of our MOS transistor, then we are going to get the area, which is like the width times the length, proportional to width times the length of the transistor, is going to scale by 0.7 squared, which is 0.49, which is about half. So we're going to get double the density. We're going to save half the area versus the previous generation. So we're going to go smaller. So that's why we want to scale by 30% each process generation. But the important point that Dennard said, which has become more prominently important in the last number of years, is that he also showed, and we all learned this except for like Eliana and Victor and Mark, who are going to be learning it this semester, that the power density stays constant. And that's maybe the most important thing here, or at least it became the most important thing. So despite the fact that we keep making these transistors smaller and smaller, therefore in the same amount of area, we can pack double the amount of transistors every year. And remember, in 10 years, that's 1,000 times more, right? In 20 years, that's 1,000,000 times more. But we still get the same heat dissipation in that type of area. And that's really important because any heat that's made over there, we have to take away. We have to cool it off. And that's what Dennard's scaling was all about. And that's why we were able to keep up with Moore's law for so long. But there was a problem, and that's, as I said before, performance is what sells computers. And Denard's law was very convenient, very conservative on the amount of performance gain that he showed that you could get, okay? And so what did people do? They wanted more and more clock speed. And if we look at the clock frequency over the years, when I was growing up and every year I'd get a much, much, much faster computer, okay? And I went from an 8 megahertz computer to a gigahertz computer within, the span of my, my teenage years, which is ridiculous. You can see that there was this exponential Moore's law in computer frequency. And that was not what Denard planned on. Okay, and unfortunately, if you look at how they did it, is they kept, one of the things is you kept the voltage level, the VDD, which is these triangles over here, did not scale according to Denard's law. Okay, and the feature size scaled, everything else scaled, but the VDD did not scale. And when that happens, you got to a point where the Pentium 4, which is really old, that's a long, long time ago. We're talking about 15 years ago, we had these Pentium 4s that somebody put a picture on the internet of CPU-Z running a Pentium 4. That's an old computer. And if you look in at this, what it says here, it says 8,000 megahertz. That's an 8 gigahertz clock frequency. What's the speed of your laptop over there? Maybe 2, 3, 4, 5 gigs. Nowadays, 15 years later, what happened to this exponential growth? Okay. We could run at 8 gigahertz back then. Okay. The problem is that the power and the power density went up exponentially along with this rise in frequency. And that means that we created more and more heat on the chips. And this brought us to what is well known as a power density crisis. And interestingly, this slide over here that you see on the left, I mean, it's a reenactment of this slide. It didn't originally have the little pictures of the rocket nozzle and the hot plate and the nuclear reactor on it. It showed that if we took all of our power density of the different Intel processors, because Intel was the only game in town those days, right? Over the years, it already, when this was, put out in 2001, okay, we had this Pentium 4 was really hot. It was much, much hotter than a hot plate, a plata chabat, right? That's how hot your processor is. This is already much hotter. But if we kept on going that way until about 2008, we're going to get to be the heat of a nuclear reactor on our chip. And if we keep on going, at around 2009, we're going to get to the heat of a rocket nozzle. And you can see this chip burning up. And I showed you probably in my course that people used to take off on their Pentium 3s and Pentium 4s. They used to take off the fan and it would literally go up in flames. Okay. As Pat Gelsinger stood at the on the podium at ISSCC and he said 10 years from now, microprocessors will run at 10 to 30 gigahertz. Well, that didn't happen, did it? Unfortunately, if nothing changes, these chips will produce as much heat for their proportional size as a nuclear reactor. And the reason it didn't happen was not that Pat Gelsinger, who, if anybody follows the geek news, knows was recently anointed to be the CEO of Intel, and he's doing a lot of crazy things at Intel to try and, they say, save the company, or at least save the stock price, okay? So back 20 years ago, he stood on the podium at ISSCC and came up with this really shock to the world. Said, we can keep on going and scaling our frequency, but we can't deal with the heat. It ain't gonna work. And everybody went into shock and nobody was prepared. So what did we do? Well, you guys have all gone through it. We started with a dual core, then a quad core, octa-core, hexacore, okay? So we keep on the same frequency as you can see here, keep on growing exponentially the number of transistors. Moore's law, alive and well. Ask TSMC, they'll tell you it's alive and well, at least till 2030, okay? Forget all those experts who say it's dead and everybody every day stands on these podiums and say Moore's law is dead. The guys who make the transistors, TSMC, say Intel says So this keeps on continue to grow, right? But the number of cores grows. So we keep the frequency constant and we raise the number of cores and we can get parallelism, okay? This is called the breakdown of Denard's law. And it's a really important part of computer architecture, okay? Because now we don't have that gain that we had while keeping power, and we have to do other things, and you have to think outside the box and not just use that performance gain you used to get by doing the same thing with the next process, the next technology node. In 2017, yes. Because, okay, how does it help us keep the temperature down? It doesn't put the temperature down, it keeps the temperature constant. We know there's a wall at which we can cool down chips. We can cool down a chip in your laptop at a few dozen watts, in your desktop computer at 100 watts, 100, 200 watts, in your servers, I don't know, up to 400 maybe is crazy, right? We can't go over that. But if you don't raise the frequency, you're not raising the power density. If we have parts of the, I mean, we did a lot of things since then, right? We have voltage and frequency, dynamic scaling. We have all kinds of things, shutting down cores, you know, big little architectures. There's lots of ways to try and cool things down. Okay, you can go into turbo and raise, you know, your voltage just for a second and then put it back down when you finish your computation. Okay, you can do other things like on GPUs, they have actual like liquid air conditioning type things, but they don't want to do that on your laptop, right? You don't even want to have a fan in your laptop for that. Okay, and for sure not in your phone. So basically parallelizing things, we can keep the single thread performance, the amount of work the number of instructions per second or whatever that you can do on your single core will stay kind of constant, but you can put a lot of those working at the same time. Okay, and then you don't go through the wall with so much power in one little area. All right, so these two guys who are shown here are Hennessy and Patterson, and you may know them because in your any computer architecture course you read their books, and if you heard the word RISC before, you know these are the guys who did it. I think that Patterson came up with the idea of RISC, and Hennessy I think came up with MIPS, okay, which was the first commercialized or the most popular commercialized RISC processor until ARM came around. And they were, in a strange, uncannily way, awarded with the Turing Award, so that same Turing we learned about an hour ago, in 2017. And why do I say it's strange? Because engineers and chip guys are not given the Turing Award. The Turing Award is given to mathematical computer science guys, but they were giving it because they really had a great effect on things that happen in the scientific world. And their Turing Award talk is called A New Golden Age for Computer Architecture, Domain-Specific Hardware Software Co-Design, Enhanced Security, Open Instruction Sets, and Agile Chip Development. And you can watch it on YouTube, okay? But I wanted to point out here, one thing they're saying, it's a golden age for computer architecture, because all of a sudden we don't get these gains just because Moore's law gives us better performance and more transistors every year. We have to think outside, okay? But one of the things to do is not only to put more and more general purpose cores on our chip, we've got to go and make what we call domain-specific architectures or accelerators, okay? So that means that we have certain parts, hardware, on the chip that does specific tasks. It's not a general purpose Turing machine. It can do a specific computation, but do it much, much more efficiently. That's both fast and less power than a CPU doing it instruction by instruction. And as you can see here, this is one of the latest Apple SoCs. And all of these boxes are different areas. That's not just, I mean, the ARM cores here are, you know, the CPU over here. I think these are the CPUs or something. They're a little part of the chip. All of these boxes are different accelerators. And you can see from 2010 to 2017, you went from like 8 accelerators, special blocks, to something like 40 on the chip. And it's even getting more nowadays. So really what computer architects have been dealing with, and us too as the guys who feed the computer architects with the components, is we're working on these domain-specific blocks. And that's what our course is going to be, the second half, dealing with this machine learning type of accelerator. Yes?
Today, most of the, let's say, hard computation are done usually on clouds or server. Like most computation power is done there, right?
This is a more generic question, where to do the computation. But even on the cloud and stuff like that, actually,
There's still a
you know how we have a good question and an excellent question? What is that? That is a Google TPU. What is a TPU? It's a domain-specific system, chip, accelerator, that's on the cloud. So when you send a query to Google, it's going to be doing your inference probably on a TPU, okay? So the question of where to do the computation is an important and good question. It's not contradictory in any way to the fact that you need domain-specific architecture. We need it on the cloud and we need it on the edge.
Like on your CPU, also on the host, you need also some computation power.
For
Or
sure.
only the-
No, for
the
sure.
Very high speed services.
No. Well, okay, let's say I talk to my Google every day and say good morning and stuff, okay? If everything I do with it, if I say, hey, Google, and it has to go all the way to the cloud to wake up, it's gonna take a long time and it's gonna bug me. So that type of thing I have to do locally. Maybe if I do a Google search, it's gonna go out to the cloud, right? And that's for sure on your phone or whatever. When you play your MP3s when you're running, it's not going to the cloud, right? But you don't want the battery to die, so you don't want the CPU to be running that. So you have an MP3 decoder, you know, an accelerator to do that. Okay, that's been there for a long time. But now more and more things are just, we have lots of silicon real estate available because Moore's law has enabled us to put a load of transistors on the chip. Well, let's use them for efficient computing. How to divide the things up, that's why it's a new era or a heyday of computer architecture, because that's a huge question, right? Where to do things, how to do things, that's really important. In your autonomous vehicle, are you supposed to do these things on the cloud where you have all this power? Are you supposed to do it locally where the latency will be low? And these are questions that are ongoing all the time, okay?
But isn't it a setback? While you discussed the history part, you told us that there are big computers, application specific. Now you told us that the CPU was the main, step forward.
First of all, it worked for 60 years, right? So I think it was a big deal. Second of all, the CPU, we're not throwing away the CPU, okay? The CPU still is this Turing complete machine that can do anything. But if we can go and offload the CPU with things that are more efficient than it, then great, okay? When we say you do things in software, it means you're running it on the CPU. And that's many orders of magnitudes less efficient than doing it on a specific accelerator. Okay, but the CPU still has its important place. And if you go to Intel, they will do all they can to convince you that the CPU is better and more important than anything else by doing the same thing. And they're working hard to make that happen. And I'm not saying that they're wrong. Okay, in many cases, they're right. In fact, I mean, GPUs are running the heavy load of machine learning stuff on the cloud, okay? And there's a startup, I think Israeli even, not sure if it's Israeli or not, that has developed some sort of a modeling technique and software package that they say that the CPU that you buy from Intel can do just as well as the GPU. Sounds like science fiction, it sounds like crazy, but they've raised a lot of money with that claim. Is it going to happen or not? Intel hopes so, okay? But Intel's also developing GPUs, right? So, and Intel bought Habana, okay? So, I mean, I don't think there's one right answer, and I for sure can't give it. If I could give it, I would know where to put all my money. But there sure are a lot of chances and a lot of cool things that can be tried and done.
They're also doing crypto.
But that's a domain-specific accelerator, right? So what we show here is a TPU. So that's a tensor processing unit. If we had CPUs, right, a central processing unit that can do anything, and a GPU, that's a graphical processing unit that can do anything, but mainly for doing very highly parallelized workloads like graphics, okay? Patterson, actually, he led the team that made this Google-specific one for their data centers that all it does is it does matrix multiplication really well. which is what you need to do for different machine learning things. And they already have, I think, 4 generations of this, including one for the edge, and it uses these systolic arrays, and maybe even, I don't know if Hanan and Or will talk about it in their Salamandra talk, but this is something that all of the research groups are doing, right, Eliyahu? I mean, and for sure, all of the companies, and there are lots of companies that are making AI chips, they're doing these systolic arrays, which are inside the GPU, and it's really cool. Okay, so that was how we're solving performance by parallelization and by domain-specific architectures, but we have another problem, which is yield. Okay, so if you remember, or you're going to learn about the cost of a chip, we saw that the cost of a chip is proportional to the die area to the power of 4. I don't know how accurate that number is. Maybe Or can tell us because he dealt with yield. But the bigger your chip is, the worse your yield is going to be, and exponentially, and with a high exponent. It's really, really bad. So we can't make good big chips. Okay, and we want high yield. So if you look at this graph over here, you see that the size of the chip, the bigger it is, the yield goes down, and this is not a linear graph, okay? And what we can see if we look at this graph over here, we see that if you look at GPUs over the years and over the different companies that make them, and GPUs tend to be some of the biggest chips that you have out on the market, they don't go higher than something like an 800 millimeter chip, and they still make a lot of them much smaller. Why not just make the biggest chip you can get on a reticle? Because you get hurt with the yield, and then the cost is much higher. So these guys who are up here at the 800 millimeters, they cost a lot more than other things. Okay, so even though we do try, and like Apple, who sells the M1, the M1 Pro, and the M1 Max, and the big difference is the die size, okay? In fact, in some way, they actually just duplicate their same design to make it bigger. But the difference is that this chip costs a lot more than this chip because of the yield, okay? And if you look at Intel CPUs, they've stayed pretty constant on their die size over the years. And that's all because of this yield problem. So what do? Well, you could go to the extreme. And the extreme is go even bigger. And this is the biggest chip ever made. The company called Cerebras, which completely went outside the box and developed, along with TSMC and with many other companies, a way to make a wafer scale engine, they call it. It's a whole wafer that is one chip. If you want, there's a talk from Hot Chips 2019, I think, on YouTube, where one of their guys explains how they did it. It's really an amazing engineering job that this company did. But they have, where the largest GPU is this size, and has 54.2 billion transistors. This was probably a year ago or so. They already have more probably nowadays. And it was an 826 millimeter piece of silicon. Instead, we get this nice dinner plate, which has 46,000 square millimeters of silicon and 2.6 trillion transistors. Okay? It can get 40 gigabytes of on-chip memory. Most of this thing is just memory. By the way, most of our chips are just memory. Okay? Most of this is memory. They want as much memory as possible to have as large AI models as possible on the chip. And so they decided we'll make the biggest chip that the machines and the fabs can make. And that's what they did. Okay? This is in a 7 nanometer process. So there is actually I don't know how much this thing costs, but it costs, believe me, it costs a lot. Okay?
How is this reliable?
Watch the Hot Chips video, they explain. There's a lot of redundancy and a lot of engineering tricks. But they're the only company, as far as I know, doing it, which means, like everything that a startup promises, you have to take it all with a grain of salt until everybody's doing it, okay? So that is an extreme way to do it, and it's for sure not the solution that's right for everybody, because not everybody's going to pay tens of thousands of dollars for a single chip. So what most of the companies are doing nowadays, including Intel and AMD, for example, is what we call chiplet design, okay? Instead of making one chip that does it all and putting everything on the chip, which we've all learned about why it's really good, well, we can go kind of in a middle fashion. We'll try to put several chips really, really close, tightly connected, and have really fast interconnect between them. And the way to do this is we take an older process like 65 nanometers and use it as a substrate that mini chips are going to go on. So we don't do any crazy fabrication of transistors on that substrate, but we do make our backend layers and through silicon vias that enable us to make the wires, to print out the wires with a VLSI process instead of a board design process to connect between chips. And we put the chips that are much smaller on top of it and have them connect to each other through the substrate. So we can, instead of putting, like Intel now sells you an integrated GPU, so you have your CPU and your GPU on the same chip, and we want it to be 400 millimeters or something. Instead of that, we put the CPU on one chip. Now it can be smaller and cheaper, or the same size and much more powerful. Next to the GPU and the I/O, which takes up a lot because it has to be analog and use higher voltages and so forth, we can even make it with an older process. And they're all connected through below here, underneath. And we can do this to the extreme. And really, most of the companies are doing this. TSMC and other fabs and stuff sell processes for doing this. Okay, it's actually, I was planning on making a whole lecture about the different fabrication, but I ran out of slots in the class this semester. But eventually, maybe we'll have some sort of talk about these types of 2.5 or 3D fabrication and the different options that are offered by Intel, TSMC, and so forth. So what you can see is we have this substrate, which is what connects to the package, and you have the wiring that actually goes through the silicon to the different dies. That's been used for several years now, but it's getting really popular. I guess it's getting a little bit cheaper. It makes the whole system integration much more complex, but the yield goes way up. And in the end, you get, if you do it right, you can get a cheaper and better product. Intel showed last year this process called Foveros, which is true 3D stacking, where you actually put one die on top of another, okay, and you connect them again through some sort of, here, this whole plane is just for connections between chips, okay? There are all kinds of issues here with heat dissipation and all kinds of stuff, but it really gets you very, very good and amazing connections. And that's called 3D stacking. And TSMC, I think they call it 3D IC or something. They also sell a process that does this, but not many companies are doing it yet. Okay, but for sure, in our really near generations, everybody's going to be doing this, or at least whoever wants to get really strong and complex systems. Is 3D new? That's a question. Oh, wait, one more before that slide. There's the next step, which we would call monolithic 3D, which actually this Israeli entrepreneur has a company called Monolithic 3D that holds a lot of patents on this stuff, where what you do is you build a layer of transistors and then you bake another wafer onto it, basically. Then you cut down the wafer and you build another layer of transistors on top. So you keep on reprocessing the same thing, and you have these really nice through silicon vias that go from one wafer to another, and you get a monolithic one single piece of one single process, but it has several layers of transistors, something like you can see here. Okay, a really nice paper by a guy who has an Israeli mom named Max Schulacher. He's a professor at MIT, one of the top students ever at Stanford. He has several Nature cover papers. One of them was this, where he showed how he stacked several different dies on top of each other with different technologies, CMOS on one, carbon nanotubes on the other, sensors on the other, memory on the other. Really cool stuff. Okay, so maybe we'll be seeing that in the future. I don't know. So far, the big guys are not playing in this field, as far as I know. They might be playing with it, but they're not showing anything. So is 3D new? And the answer is no. What you see over here on the left is what you have in all of your cell phones and all of your hard disks, and this is 3D NAND, okay? The way that Flash has continued living way beyond its lifespan is because they started stacking it in the third dimension, and you have these monolithically integrated processes that go on top of the other, and it works because Flash is very regular, okay? The other thing that you have is high bandwidth memory, HBM, which you find inside GPUs and so forth, which is a way to get more DRAM on your chip. And this uses this 2.5D on one side where you have the GPU or CPU or something on the same substrate, on the same shared interconnect substrate as your memory, but then the memory is stacked on top of each other. And again, they use this fact that the DRAM chips are exactly the same and they can make them so you can stack them, and they have 8 or maybe even 16 now dies of DRAM stacked on top of each other, so you can get a lot of memory really close to your processor. But that's only semi 3D. It's similar to whatever Foveros and stuff is. They're working on something called 3D RAM. As far as I know, there are no products yet, where if with DRAM, you have this stacked or trenched capacitor. So this is a stacked capacitor. This white thing is the capacitor that goes way up to get this high capacitance you need in the DRAM cell that sits on top of the transistor. Well, why not just turn it on its side? And then you can make as many stacks as you want on top of each other, and each one of these is a cell. And the area doesn't matter how many of these are stacked on top of each other. It's going to still take up the same area for a single stack of DRAM. So that's something that they've been working on for quite some while, and it might be another way to get much higher density in DRAM. And with memory, if we're already talking about memory, there's something called emerging memory technologies. So if we talked about those beyond more transistors, with memory, it's much more advanced. And we have all of these types of memories that could be replacing DRAM, though probably not, could be replacing SRAM, though really probably not, but for sure will be replacing NAND and hard disk and so forth in the coming future. And you have different things like memristors and like magnetic memory that you already have products in the market, and we'll be seeing more of them. We've been promised to see more of them during the last 10 years, but we'll for sure be seeing more of them, I think, in the near future. With that, we have Intel, which came up with Micron, even though, as far as I understand, Micron kind of left this. They put out a product called Optane, which is phase change memory, which they actually sell as either instead of a DRAM DIMM or instead of an SSD, and you can even have it sitting on top of your chip, and it's really fast non-volatile memory. So it's really the first of these emerging memories that has come to a product that we can actually go out and buy. It's still not sold much for our like personal uses. It's still too expensive, but eventually I guess that if it succeeds, then the price will go down and we'll all have it on all of our laptops.
Highly successful, the cloud service.
With cloud servers, of course, where you can pay more for the chip, then they're willing to pay more for this extra speed and non-volatility and so forth. So with that, we finished the present and the kind of near future. And the question is, what does the real future hold? Okay. And there's this graph that I found that I'm not crazy about, but it tries to put a picture of what the vectors of research and development are working on. And you have on the x-axis what they call new architectures and packaging. Okay, so starting from our like general purpose, our traditional processor that was our workhorse for 60 years or whatever, maybe more. Okay, we went first of all to the SoC, where instead of just having a processor on a die, we have many different functions on the same die, and we keep on going through this 3D stacking and all kinds of things, reconfigurable computing and stuff like that. We have the y-axis, which is the new devices and materials. So after having CMOS for all these years, from I guess the 70s until 2011, when the Tri-Gate came out, and I guess you could still call what we have now CMOS, we start having other things like TFETs and piezoelectronic FETs and photonic ICs and carbon nanotubes and graphenes and spectronics, until we want to get to some sort of a switch that uses an attojoule for each switching operation, right? And then we have this vector in the middle that kind of looks at computation differently. So it looks at approximate computing, you know, maybe data flow computing going backwards, neuromorphic, analog computing, quantum computing, and so forth. So this is a kind of way of spreading out the space of where different research and development is heading, and some sort of mixture of these types of things is going to give us the computers of the future. So some of them that I just wanted to point out that are being heavily researched and worked on, one of them would be neuromorphic computing. So neuromorphic computing is not the AI as we've been doing it today, which is, I guess you could call it brain-inspired computing more, which is doing machine learning, but it's not doing what the brain does. Neuromorphic computing is trying to see how the thing that's in our head works, because our brain is very, very highly parallel. We have all these synapses that are working at the same time. There like millions of them, right? They are not only storing the data, they are also doing the computation in the same place. So that's in-memory computing. It happens in an analog way, not digitally. They're plastic. They can learn and change over time. They can change their connections. Okay, a lot of it's probabilistic. They don't your brain doesn't figure out things necessarily accurately, but it does it good enough. It's scalable, so you can get, you know, huge amounts of information. It's sparse. Not every synapse is connected to every neuron. Okay, it knows how to learn. Hopefully, what you're doing now is teaching your brain, and it's very non-linear. It's not like a standard computation, which is very linear. And this is very tough. There are lots of projects trying to do this. One of them, a very famous one, okay, is called True North, which is a project funded by, I think, $1 billion or something by DARPA, led by IBM, that they put out a few years ago, which shows 1 million of these neuromorphic neurons, which can do a 73 milliwatt power consumption for doing all kinds of machine learning, all kinds of artificial intelligence type of tasks. So remember, our brain does this at a really slow frequency and with hardly any power consumption. And what we're doing now on our GPUs and our TPUs is burning out the power of the world, right? So this is where we want to try to go to see if we can do something that's really, really orders of magnitude more energy efficient than anything we're doing today. Yes, Ariel. This is not neural networks. It's a completely different institution. Memristors can also be used for this in some ways or another, but most of what memristors are being used for now is like matrix multiplication in memory.
I heard about the, I think, spiking neural network, I think.
Spiking neural networks are something that's more neuromorphic computing inspired. There's a lot of research about this. It's more on the analog side, I would say, than the digital, but there's some people who say it's wonderful. Some people say it has no, that it's not going to work. In the meantime, when something works really well, like neural networks, then it leaves little, like, okay, 3D stacking of flash, it leaves little room for emerging memories to take over. You know, we still use these magnetic hard disks. Why? Because we keep getting cheaper and more dense, right? So, what? Yeah, so it should have died 30 years ago, and we still have, you know, you still buy a computer with a regular spindle magnetic hard drive, right? Okay. The second vector I want to talk about was photonics. So this is really interesting, and I think this is amazing. This chip over here, it says on it LM, which stands for light matters, I think, light matter. They are using photonics not only for what we've been doing traditionally for a long time, which is for communication between systems. For any high-speed communication that's at least longer than, you know, very close, we're not using electricity, we're using light because it's much more energy efficient and fast, okay? These guys are doing neural network computation with light. So using all kinds of refractive characteristics of light, they're doing matrix multiplication. They claim they're doing it, you know, orders of magnitude faster than anything we do on chips, on CMOS chips, and with a lot less power. They have products that they sell already. I'm intrigued by it, okay? But we also have silicon photonics, you know, using everything we learned about silicon, but about the processing, because silicon, you know, we know how to use sand, right? Go and use it for the optics. It's not the perfect waveguide, but it does work. And there's a lot of work and a lot of products with silicon photonics. Of course, communication and storage, okay? Storage you can also do with light. Yeah. I imagine that if it was reliable, then the chip guys wouldn't have a job, or the AI chip guys. I don't know. There's one company, as far as I know, that has such a product, and it's a startup. It's not a, quadrillion-dollar company. So, Eliao, I don't know much about it.
Conference last summer, some of our researchers here talked about some optical chips, and they really discussed about the reliability, how they can preserve the memory for at least microseconds.
Look, there's a big difference, and Or will tell you that, between what has been shown on one device in a lab and to go to a scale where it's usable. Look at quantum computing. Half the world is working on quantum computing, which is probably our next slide. But we still don't have a quantum computer that is doing what the potential is. Okay, we have a call out for 500 million shekels, I think, now from the Israeli government to develop the Israeli quantum computer, and that's like a few orders of magnitude less than what we need and what other governments have put out. But everybody's working on quantum computers. Is it going to happen? There's a really good chance now that I can say yes. Has it happened with the years of development that have been and the money that's been put in? Not exactly. Okay, so in the lab or in demonstration, you have things, but we haven't even really reached quantum supremacy, okay, which is the ability to do a single type of computation faster than any computer, supercomputer in the world can do within in the lifetime of the universe. We haven't reached that. There's work by Google that they show quantum supremacy in 10,000 other research groups who don't want Google to win the race, who have shown that what Google's doing is not true quantum supremacy. So, and that's not a true quantum, some sort of general purpose or some sort of real applicable quantum. That's one algorithm that nobody needs, right? Okay. Yeah, Aaron, you wanted to ask something?
Regarding the communication, so there is already communication, like you said, optical communication.
Optical communication, the whole internet runs on optical communication.
On board, for example, it's going to be.
So yes, so the problems, and I'm not a big expert at this, is that you want to try and integrate all of the parts within the same chip or the same package, and maybe even do communication between parts of the chip with optics. And these are things that are integrated silicon photonics that people are working on, and that would make a big difference. If you could make these big long lines they're long lines, but they're a few microns long or whatever, right? You could do them with optics and not burn the power and do it much faster, then that would be really cool, right? So people are working on it. But most of what's done now is just between servers level. Okay? But it's very, very widely used. And of course, you can always do it better and stuff, I guess, too. Here in Bar-Ilan, they're big, Zev and Avi, people are big researchers in this field.
Avi, I have a question. Is also quantum computing, can you do quantum computing with photonics, right?
There are all kinds of tries how to do it, yes. I don't know anything about photonic quantum computing, but yeah, it's one of the vectors that's being tried to solve the technology underneath.
Okay.
So with quantum computing, I want to mention it just very high level. If we have a classic bit that's a 0 and a 1, a qubit is a superposition of 0 and 1. So it has this kind of infinite space around, the real and imaginary plane, which basically means that, again, according to Schrodinger's cat, you can be in superposition of both a 0 and 1 at the same time. And if you have, for example, two people, so there are two combinations of how you can sit those people around a table. That's okay, it's a big deal. We do that with bits all the time. We check those two possibilities. When you go up to 5 people and you want to check all the combinations of how they can sit around the table to seat whatever your family at a wedding, there are 120 combinations, but that our computers that run at gigahertz do easily. But when you just go up to 10 people, we're already up there. You can't even see the tables over here because there are over 3.5 million combinations. And if we have 100 people, I don't think we can check all the combinations with a normal computer. But a quantum computer, if you have 100 qubits, it checks them all at once. And that's an amazing scale. All of our cryptography nowadays is built on the fact that no computer can go and run all the combinations to find the secret key. But a quantum computer, if it's big enough, it has enough qubits, it can easily crack those keys.
So you don't want it.
Well, you want to be first. But that's the malicious use of a quantum computer. Look, the optimal routing problem, traveling salesman and so forth, you have 50 places you need to distribute your product to. You want to find the best route that will save you the most fuel and the most time. How do you check it? 50 combinations of how to go through these places. The quantum computer will do it easily. Okay? You want to know how to invest in the stock market. Right now, there are too many options there, but a quantum computer can help you solve these problems. And one of the most intriguing things is that you can do simulations of chemistry and find out drugs, how to solve cancer and stuff like that, if you're able to get the scale of computation to be able to find out these problems. So these are some of the small problems that quantum computers will enable us, okay?
You can use it even to make chips, right? Kind of process is making
That you can do with AI, you don't need that. You don't need a quantum computer for that.
still making things.
Yeah, with AI, you can do that. But sure, I don't think you need a quantum computer. Another vector that's very interesting, the last one, is biological computing. So this is a chip already from 2013 shown at MIT where they use chemical reactions, biological cells to do computation and store data and achieve computation. And there are all these different things. You can use biochemical computers, biomechanical computers, bioelectronic computers. Noah is not here, I guess, but she's working on this type of thing in her PhD and in some of the labs here in the bioengineering, they're working on this stuff. Network-based biocomputers. And one thing that is already been shown at large scales and maybe soon enough will actually be productized is using DNA for both storage and for computation. So you can take a strand of DNA and put all of the data in the world on it or something like that. Okay, and there are, I think, even products out that show how this can be done. It's already at a very advanced level. I mean, these things have been shown several years ago, and obviously there are problems and nothing is solved, but these are really interesting types of things. So those are what I wanted to show, and that brings me basically to the summary and conclusion of this talk. Okay, and what I wanted to say for the summary is show this guy over here whose name's James Kip Finch, who he is quoted as saying, "The engineer has been and is a maker of history, and that's what you guys are." And the other guy who's Abraham Lincoln, who said that the best way to predict the future is to create it. So let's go out and make history.